Hello, welcome to our channel for probability and statistics. In this video, we will talk about hypothesis testing of population mean and under the case of non-variance. So say we have an experiment sample x1, x2 to xn, which will be used to test the hypothesis h0, null hypothesis mu equals mu0 against alternative hypothesis h1, mu not equal to mu0. And we know this sample from normal distribution, and we know the variance of the population, sigma square. But we do not know the mean of the population. This is what we want to test, h0 and h1. So now the only information we have is from the sample x1 to xn. Then we can create a test statistic based on x bar, which is the sample mean. Then according to the Central Limit Theorem, so the x bar under the large sample, reasonably large sample size, say larger than 30 at least, then x bar will have approximately a normal distribution with the mean. This mean is the population, and the variance equals population variance divided by n. N is the sample size. So this means x bar centers around the population mean, which we want to test, and its variance is only 1 of n times of the population variance. So its variance is very small compared with the population variance. Then we can use this information to determine the critical region to test the population mean. So we can create a standardized x bar, which equals x bar minus the mu. Mu is the population mean because x bar centers around population mean. So this mean is also the x bar's mean. So say if we have one x bar, maybe not same to the population mean, but if we have 10,000, 1 million x bar, it will be very close to the population average, population mean. So we use x bar minus mu, then divided by standard deviation of x bar. This term is the square root of the sample variance. If we look to the previous page, so x bar has the variance sigma square. Here is the square, sigma square divided by n. So we use x bar minus mu divided by the square root of x bar's variance. Then this term, this statistic called Z, has standard normal distribution, which means has normal distribution with mean equals 0 and variance equals 1. So under null hypothesis h0, we can fill h mu0 in this formula. Then this term square root n times x bar minus mu0 divided by sigma. This term actually is this term, right? Just transform square root n in the numerator. and fill in mu0, which is the value we want to test. Then this statistic follows an also normal distribution, standard normal distribution with mean 0, variance 1. So then what we can do next? If this term follows standard normal distribution, then this term's probability between two values equals this probability. And these two values called critical value under the alpha significance level. So if we use 0, 0, 5 as the alpha for the significance level in a test, then the probability of this standard normal test statistic between these two critical values, this two critical value is critical value for the half alpha. So this term between the say 0.025 and minus say 0.025, probability is 0.95. So if we look at this figure, maybe more clear. So this is the X bar, and the probability of a standard normal distribution is a transform X bar will surround around the 0. Here will be 0 because we use a standard form. So X bar minus mu divided by the square root of its variance. So here is 0. So the larger part of this test statistic in the white area is about 0.95. But we cannot exclude the small probability of X bar's test statistic located in this shaded area. So the hypothesis testing is if we calculate and get the Z value, we use X bar in this form, X bar minus mu 0 divided by the square root. And if this Z value in these two areas, then we will reject H0 and we will in favor of H1. So which means the population mean does not equals to mu, right? And if we get the test statistic say in this white area, which means say between negative say half alpha and positive say half alpha, this value, if in this white area we will not reject H0. So if we look back, so H0 is mu equals mu 0 and H1 is mu not equals to mu 0. And also this alpha, so half alpha and alpha 0.05 here also called type 1 error. What this mean? This means although from the sample we find the Z value located in this, either in this shaded area or this shaded area, then we reject H0. But it is also probable that H0 is correct and we got the sample in this blue area. Then we commit an error. This error is we did wrong rejection. We did the wrong rejection of H0 and when actually it is true. So this probability should be very small because people do not want to make rejection wrong always happen, right? We have to make this as small as possible when H0 is true, but we reject it. So usually that's why alpha is set to 0.05. It's a very low probability that we make a wrong decision. So this is called type 1 error. This is why we set a critical region in both ends of the density curve. We do not set alpha here, do not set alpha here. We set here very small, this is only 2.5%. 2.5% here also. The total only 5% of the total probability that we can make and type 1 error. So this is also called significant level alpha. So next we show an example to calculate and test a single mean. So manufacturer of sports equipment has developed a new synthetic fishing line that the company claims has a mean breaking strength of 8 kilograms with a standard deviation of 0.5 kilogram. So this is the population mean hypothesis should be tested and variance known, right? Standard deviation of the population known. Then test mu equals 8 kilograms against the alternative hypothesis that mu not equals 8. So from the random sample, 50 is tested and found to have a mean break strength of 7.8. So 7.8 is a sample mean sample average, and use a 0.01 level of significance. So here the significance level is more strict than before, than 0.05. So the solution is we just establish two hypotheses first. So H0 is mu equals 8. H1 is mu not equals 8. Then we set alpha significant level 0.01. Then from the standard normal distribution we find for alpha 0.01 we find a critical value say equals minus 2.575 and positive 2.575. So if we look back, so 2.575 is almost here, right? Because this is 1.96 minus 1.96 for standard normal distribution. To leave the area is about 0.025 here. But if we get the total alpha 0.01, so this area should be 0.005, right? 0.005, almost here. 1/5 of 0.025, right? So 0.005. That's why we get the value minus 2.575 and a positive 2.575 here. These are two critical values located almost here and here. So the blue region is smaller than the area shown here. Then we can use this form, x bar minus the population mean tested and the population variance divided by square root of the sample size. So fill in x bar and sample size, we can find the z value. Test statistic z value is minus 2.83. So because 2.83 is less than, say, less than minus 2.575, right? So which means we have found critical value here. But the test statistic is even smaller than this negative value. It's even on the left side, right? Further right to the left side. So on the left side of this critical value. So that's why we reject this null hypothesis and will in favor of the H1 hypothesis. Actually, will in favor that the mean of the population is less than 8, because we get a negative, right? Less than 8. And also, you can calculate the p-value. So p-value is twice the area of the region to the left of this one. Say, so we use p-value equals the probability of the absolute value of, say, larger than 2.83. So 83 is here. We find the say value from the test sample, test statistic. Then we calculate the p-value of the absolute value larger than 2.83, then times 2 of the probability of z less than minus 2.83 equals 0.0046. We should see this figure again. So we calculate the p-value because the critical value is 2.575 here, which leave 0.005 for the probability left area of this critical value and 0.005 of the probability right of the critical value, 2.575 here. But we get the value, get the test statistics minus 2.83. It's even smaller than 2.575, right? Even smaller than negative 2.575. So 2.83 almost here. Then we calculate the p-value is the probability on the left side of the minus 2.83 in the blue area. So very small. Then we have the time 2 because we use 2n test here. See, so this one very small, also plus 2.83 right of the 2.83 in the positive side. So plus these two right left blue area, then we get the p-value is about 0.0046 because the p-value is less than 0.01. So is rejection, the null hypothesis, is our conclusion. So hypothesis test, you can use say value. So find if the say value is less than in the two-tailed test, if say value is in the critical region, which means less than minus 2.57 or larger than positive 2.57. So we reject in the critical region because the say value located in critical region. And the p-value approach is if we got the p-value associated with this test statistic in a normal distribution is less than the significant level we defined. So we specified 0.01 is the significant level of the test. Then we got the p-value smaller than this significant level. Then we also reject. So both will come to the same rejection, right? Thanks for watching.